by a factor of 8. You, even worse. Big, big, big. Give a whole too small. Big, big, big. Big picture. Big picture. Big, 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 big picture. No, not too small. Big.
What do you? How big do you want it?
Very big.
Take half the paper. Okay.
He wants it.
He wants it big. He wants it big.
You know what I'm talking about. I teach this crap every year, and there's a lot of people who just get problems wrong because they just can't tell what the hell's going on because their picture's so small they can't even see anything. I insist. Okay. A water tank has the shape of an inverted circular cone with base radius 2 and height 4. Water is being pumped into the tank at a rate of 100 cubic meters per minute. Find the rate at which the water level is rising when the water is 3 meters deep. Okay, we have a lot of stuff going on here. We have water leaking into a cone, or a conical tank rather. Remember all the steps. Read and understand the problem. Draw a picture. Pick variables for the quantities which are changing. What quantities are changing in this problem?
The amount of water left in the or the amount of filled with water.
Okay, we have to be a little bit careful. Wait, pause one second. Gabe, you said radius, right? But that's a little bit like vague. What do you mean by, when you say radius, what do you mean?
Basically, like the radius of like the water.
The volume of the...
Yeah, wait, one person at a time. Yeah, he got that. But he found it kind of awkward to say. Because the tank has a radius, right? What's the radius of the tank? 2. But R is not the radius of the tank. R is like the radius of the like cone of water. That already requires some actually understanding of what's going to happen. If you partially fill a conical shaped tank, then the water in the tank is itself going to be like a cone, right? Okay. So when you guys, when he said, is that kind of what you were thinking, Gabe?
Yeah.
It's worth it to take the time to like articulate it, at least like to yourself. So let R be the radius of the cone of water. So this is all like water. Okay, good. And what are the other quantities which are changing?
Oh, H for height.
Yeah, that H be the height of the water, or of the cone of water. Okay, so that's H. And probably one more even. The volume is the other thing, right?
Or volume of water or volume of like, I guess volume of water. Because
yeah, this is a little tricky, right?
Cone. Like
I could calculate, so what do I know about this thing? I know that the height of the tank is 4. The radius of the tank is 2. But I don't really think there's any point in calculating the volume of the tank, right? I don't think I need that. Because what do I want to actually find?
The rate at which the volume is changing.
Right, yeah. So let R be the radius of the cone of water, let H be the height of the water, and then let V be the volume of the water, of the cone of water. Okay, so read and understand the problem, pick variables for the quantities which are changing, make a picture, add those variables to your picture. Now let's translate the information given in the problem and the information requested in terms of those new variables. So what are we given?
That's being pumped into the tank.
Yeah, in particular,
100 liters.
yeah, but what is 100? In words you said it correctly, but let's translate it into math language. Yeah. Yeah, it's the rate at which the volume is changing with respect to time. It's a minute, right? Cubic meters per minute. Yeah. So, I mean, Dia, you're right that it's the rate at which the water is coming into the tank. But once we define V to be the volume of the water, then that is just what dV dt means, right? dV dt, the rate of change of volume with respect to time. Okay, and what is it that we want? Someone besides Wenson. It's always Wenson.
What?
Yeah. dH dt, but specifically at h equals 3. Yeah. Okay. Everyone good? All right. So now, now that we've figured out what it is that we're actually trying to find, we need to find a relationship between the variables. So what is the relationship between the variables?
V is equal to 1/3 pi r squared equals h, except now there's 3 variables.
Yeah, good. Ryan Cho says, I know the formula for the volume of a cone. It is 1/3 of the volume of the corresponding cylinder, so it is 1/3 pi r squared h. But now, he is all panicky and, yeah, jazz hands, because he's like, oh, there are multiple variables. Does everyone see how this is like quite tricky, right? Now volume is like a function of two things. It's a function of the radius and also the height. So whereas previously on the first page we just differentiated now, if I differentiated now, does everyone see how it would require like ugly product rules and things would get really like weird and complicated? I don't think I want to do that. Is there, pause Ryan Cho, is there yet another relationship between these variables?
Indeed.
Indeed there is. What is the other? Take a good look at your very high quality picture and see if you can determine, using common sense or otherwise, that perhaps V, R, and H have another relationship besides this relationship. Similar triangles. Yeah, who knows what he's talking about? Notice that this is not just any old tank. It's a particular tank with particular dimensions. And thus, based on the shape of the tank, we can predict the shape of the cone of water that will be partially filling that tank. Does everyone get it now? In other words, the cone of water is similar to the cone of tank. Okay, so someone, Casio, what's the relationship then? What's the additional relationship we have?
Like H and 4 and R and 2.
Yeah. Yeah, she says the height of the water has to be to the height of the entire cone, as the radius of the water is to the radius of the entire cone. Yeah, maybe even simpler, like what's the relationship between R and H?
1/2.
Yeah, H has to be twice the radius. Does everyone see that? So yes, you do. Yeah. Because the height of the cone is always twice the radius, so the height of the cone of water has to also be twice. Okay, so good. This enables us to substitute in to rewrite this as a function of just one variable. And which variable should we get rid of? R or H?
R.
Definitely R.
No, I think we should get rid of R because we want dH dt. So we want to keep H. Okay, so let's do this before the bowing. We get pi over 3. In place of R squared, I'm going to write
1/4 H.
R, yeah, R is H over 2 squared times another H. And now I have succeeded, by finding an additional geometric relationship between R and H, I've now succeeded in expressing volume as a function of just one variable. Are we cool?
Yeah.
I'm missing some of the spirit of period 6 today because of fam club. Okay, so simplifying this, what is that, like pi over 12 H cubed?
Meters per minute.
Right, Joe, pi over 12 H cubed, right?
Wait, what?
Yeah.
Yeah, good.
That's right.
Good. Now we have succeeded in establishing that V and H for this particular cone must have that relationship. Now what?
Now you just do it.
Now you just do it. Pixie dust, sprinkle on. What does do it mean? Take the derivative of both sides with respect to
T.
t. So dv dt equals pi over 12 times the derivative of h cubed with respect to t, 3h squared, back inside dH dt. Oh yes. So it's like pi over 4 h squared dH dt. Okay, and now we just finish it off more or less. So what is, let's see, what is dH dt? dH dt is like 4 dV dt over pi h squared. Did I do that right? Yeah. Okay. So that's in general, but also I know what dV dt is. It's like 100, right? So that gives me that dH dt is 400 over pi a squared. And now I'm almost done. I don't want dHdt in general, I want dHdt at a particular point. So what's I can do? You just plug in 3, right? So the final answer is dHdt is 400 over 9 pi, and the units are like meters per minute.
Why do you still have G? How old is this? Oh yeah, she still has her multiple.
Nice.
You know how my mom educated me? She made me.
Okay, guys, say goodbye to Envirothon people.
She made me